Hello class, this is a lecture on HL radioactivity. We're going to focus on different experimental setups that helped us understand more about different particles, energy levels, atomic radii. In order to do that, I wanted to go back to radioactivity we learned in SL, the core content, and that is alpha decay, which is when nuclides release, due to instability, a alpha particle, which is a helium nuclei, 2 protons, 2 neutrons. The next decay was the beta decay, which either produced a electron and an antineutrino, or a positron and a neutrino, and this occurred due to proton-neutron imbalance, and therefore the nucleus was unstable. And gamma decay, which is just a release of a photon, a high energy photon. This occurs when an atom is either excited, or it is excited, and it's excited just because of, another photon interaction with it, or it could also be due to one of these other radioactive processes that leave the atom in an excited state. Now that we've covered that, I want to go and talk about some of the experiments that led us to more information. The Geiger-Marsden being one. This is something that we've already seen before. This helped us provide evidence for a central nucleus. This is the one where alpha particles were shot at gold foil, and most passed straight through, some were deflected, and very few got deflected backwards. Now the ones that deflect backwards, that's the ones we're going to focus on in this. So let's look at those alpha particles. They were shot off with some kinetic energy. There is an electric potential energy that the kinetic energy is trying to overcome to pass it, but it doesn't. There's, if it's close enough, it will feel a repelling force. Some will be deflected, and then some will even be shot backwards. So let's imagine in this situation that we actually have the ability to shoot off these alpha particles with higher energy. What we found is they didn't deflect at all. We found that if we were to give an alpha particle so much kinetic energy that at some point in time it doesn't, even if it's going directly at the nucleus, it does not deflect backwards, and either it passes through, it interacts. That's not what we're focusing on. What we're focusing on is what's the minimum kinetic energy for it to not be deflected backwards. And this energy is going to help us determine a distance of closest approach using our understanding of energy, which is going to be pretty much our approximation of a nuclear radius. So let's go to the experiment, like a relationship that we noticed in this before we jump into the equation that we'll see. In this graph, what we're seeing is the amount of alpha particles that are backscattered depending on the amount of energy that are shot. So at the beginning, it follows this pattern. Let's do kind of blue, or it follows this pattern. It's going down, going down, going down. And that means that when there's less kinetic energy, it has the inability to overcome the electrostatic force. So more are going to be bounced back. More are going to be observed being reflected backwards, or some deflection not passing through. What you would expect is, you add more kinetic energy, then less and less are going to pass through. But at some point in time, it breaks, and when this point breaks, about right here, what we found is significantly less were backscattered. That means more and more and more pass through. Why did this occur? And we're talking about like reflected backwards, right? So that must mean that this energy is the minimum energy required for the alpha particle to get as close to the nucleus as it can. And that's where we get to the approximation. So that must mean that if we given this kind of minimum kinetic energy, it equals the electric potential energy. If it's more kinetic energy, it's going to pass through, right? That's all this shaded area, more kinetic energy. But what we're looking for is the amount that could help us determine the minimum to get to the closest distance. So this EK, right? We know what potential energy is. It's equal to KQQ over and I'm going to use D in this case, D squared, where large Q is going to be our gold nucleus. So that's going to be our charge of gold nucleus. And we're going to say like Z protons. That's what we're going to use. And then Q is going to be our charge of alpha particle, which is 2 protons. And so this is 2e, this is ZE, this is 2e, and D is the distance, right? Distance of closest approach. And we want to eventually solve for D. So if I put this in here, I get EK is equal to K, and actually, well, K, you'll see, you might need to remember this, K is equal to 1 over 4 pi epsilon naught. That's in your data booklet. We just need to remember that. So that's equal to Z2 times, and my 2's look like Z's, you have to be careful, 2 ZE squared divided by 4 pi epsilon naught D squared. This occurs, right? 2 ZE squared is 2E times ZE, right? This, the charge of the gold nucleus and the charge of the alpha particle. If I solve for D, I would end up with this equation right here. And that's the equation you'll get for distance of closest approach. They might ask you to derive that or explain it or some sort. So when you do this, if you plug this relationship in, and you'll end up finding an approximation which is pretty darn good to the atomic radius. If you do this over and over and over for a lot of different nuclei, if we have the ability to, there is a calculation that ended up being, or a relationship that matched how large the nuclear radius is for different atoms with different atomic numbers. So different, or not even atomic numbers, it would be a mass number, protons and neutrons. And that's where we get to this atomic radius estimate. So the last constant in your data booklet is going to be important here. It's called the Fermi radius. And this Fermi radius is the estimated radius of the hydrogen atom. Fermi determined this and was able to, in experiments, find out the radius of other atoms. And he found that the relationship followed a power to the 1/3 relationship. So R is the radius of atom, like with a mass number. So let's say that is A is the mass number of atom. Remember, mass number is protons plus neutrons. And this R, this is our Fermi radius. That's our constant. So if we're looking for hydrogen with 1 proton, 1 to the 1/3 power is just 1. So we get the radius of this Fermi radius. And that's where we get this hydrogen atom with, like, this is actually a 1 proton hydrogen atom. If it was 1 proton and 1 neutron, it would be 2 to the power of 1/3 times this. So let's estimate the atomic radius of a cesium-133 atom. So we see cesium-133, that's our mass number. So I know R for my cesium is going to be my 1.2 times 10 to the negative 15th. Oh, this is good to know, just in case there are questions in multiple choice that ask you to relate the radius of an atom or size of an atom to something else. This is the order of magnitude. So the Fermi radius can help you determine the order of magnitude. Now, of course, when it gets larger, it may get bigger, but this is just a good rough estimate. So you can use times 10 to the negative 15th for all estimates of size of nucleus. So R equals 1.2 times 10 to the negative 15th times 133 to the 1/3 power. And this would leave you with 6.12 times 10 to the negative 15th meters. So that's our radius estimate, radius for our cesium-133 atom. Now I want to find the density, and this leads us to an interesting understanding of how dense these atoms are. So, well, density, right, that's equal to mass divided by volume, where mass is equal to the amount of protons and neutrons times U, and our volume is, what, 4/3 pi r cubed. But we have just found that our radius gives us a cube root. So I can plug that in as I get A times U is equal to 4/3 pi, and then this is R naught A to the 1/3 cube. Well, the A to the 1/3, so it's kind of let's make that a little nicer. This is 1/3. The A to the 1/3, those two cancel out, and we end up with A times, and might as well move the 3 up to the top. 3AU over 4 pi R naught cubed times A. The A's cancel out, and I end up with a density of 3U over 4 pi R naught cubed, and these are all constants. And if I plug these in, I would end up with 2.29 times 10 to the 17th, and that's kilograms per meters cubed. 2.29 times 10 to the 17th, that times 10 to the 17th is huge. This is an extremely dense nucleus, and every single nucleus turns out to have this if we follow, like the same calculations that have been shown to be supported. And just to get an idea, though, this density of an atom is similar to the density of a neutron star, so that must mean that protons and neutrons pack very similar to like the neutron star due to the strong nuclear force. But a teaspoon of this weighs 10 to the 12th kilograms. A teaspoon, right? What is that? A million kilograms in 1 teaspoon. So that's super, 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 super dense and very improbable, but that doesn't mean not possible. It's just kind of unclear to us as humans. We're going to now look at alpha decay and beta decay and how they led us to some more understandings of energy levels and scientific understanding. So in alpha decay, we know that it's due to nuclear instability. An atom releases an alpha particle. In this case, we have an example of americium, Am95-241, and it's undergoing alpha decay and decaying into neptunium, which is 93-237, making up a alpha decay particle, which we know have 2 protons and 2 neutrons, 2-4. As it decays, though, it doesn't just decay into neptunium's ground state. There's a lot of different possibilities for it to decay. This is observed in experiments. It decays into an excited state. Now, that only shows these sections because after it decays into an excited state, it must undergo gamma decay as well to show the decay of, or the release of, the photon from an excited atom, excited neptunium. So this second stage that occurs is this excited neptunium that's kind of gamma decaying into just ground state neptunium. So this is important because we see 2 different stages and we see 2 different forms of quantized energy. If you add these 2 energies up, we go from americium to neptunium in a energy difference, an energy, a mass difference, there is a release of energy. So we know going from americium to neptunium, there is a amount of energy that gets released. That amount of energy is made up by the quantized energy, and specifically like kinetic energy of alpha particles, and the quantized energy of photon that's being released from the atom. So this daughter nuclei, every single time there's an alpha decay that occurs, this decay, there's a parent nuclei decaying into a daughter nuclei in different energy states, and then that daughter nuclei is going to release a photon, and this helps us support more further that there are, like the support evidence for energy levels, for quantized energy levels. The next observation was made in beta decay. And as we said in the previous decay, that there must be some energy released that we can kind of confirm between parent and daughter. And that energy that's being released comes in between the change in the parent and the daughter. And that must be composed by some particles that get released, this electron and this antineutrino. Now, before, there's a moment when we didn't really know that antineutrinos existed and neutrinos existed. But in this observation, we found that during beta decay, we observed the kinetic energy of the electrons. And we found that the energy, the beta decay electrons, had a continuous amount of energy. So this is a continuous energy spectrum, that was probable in each beta decay experiment, or beta decay that occurred. Now, for this to occur, that doesn't make any sense, because the energy here must be quantized when going from parent to daughter. That's something we've calculated. So how could the electron have a continuous energy? And that is because this energy is equal to the energy of the electron plus the energy of the neutrino, in this case, the antineutrino. So this is our original evidence to predict the existence of an antineutrino or a neutrino before we were able to measure it. So this is the beginning of neutrino prediction. The next topic we're going to talk about is radioactivity and half-life, specifically focusing on the equations. In the core content in SL, we learned about radioactivity and that things had a chance of decaying, and nuclei had a chance of decaying from parent to daughter, and it followed an exponential decay graph. And in that exponential decay graph, we could determine how to graph it based off of using half-lives, every half-life being the time it takes to half the original sample. We're going to go into the variables involved in this and then the equations. So the first variable is n, is our sample size, amount of radioactive nuclei, so how many nuclei we have. A is activity, and this activity is the average rate of decay at a moment of time, and this may change depending on our sample size. We're going to see this, the units for activity is decays per second, or becquerel, BQ, which signifies, again, the average rate of decay. Decay constant is the probability that a radioactive nucleus will decay, measured in 1 seconds. And this is similar to probability of rolling a 1 on a 6-sided die. And what would that be? Well, it's 1/6, right? So if you roll a 6-sided die, over and over and over, you have a 1/6 chance of getting it. So this is a probability because radioactive decay occurs kind of randomly and through probability. Something that's not in your data booklet, but you need to be able to identify and be aware of, is that activity, the amount at which the nuclei decays, is proportional to the number of nuclei we have. So if our nuclei or sample size increases, then our activity, our decays per second, is also going to increase based off of the probability of decay. So if we had 1 6-sided die, it might take us 6 rolls to hit a 1. But if we had 30 6-sided dies and we all roll them at once, we're going to hit a lot of 1s. So we're going to have a lot more decaying. Now, something that's in our data booklet are these two equations, which compare the sample size and our new sample size and our original sample size based off of the decay constant. So the first one we're going to identify is n naught, which is the original sample size. This n is our new sample size after time t. E is Euler's number. And then you'll see two variables in here. We'll see the decay constant and time. So recognizing, right, that this decay constant has a unit of like 1 over seconds, but it's really actually 1 over time. So it could be like 1 over day, something to be aware of. It doesn't have to, because when you multiply it by time, it depends what we're using for time. So is time in seconds, or is it in days? All we care about is that when we multiply, lambda times t, that's not lambda, that this is unitless. That's all we care about. Again, seeing that a is equal to lambda n, so you see this n naught, and that becomes lambda n naught. So this is the same equation. We're just plugging that in, but this is where we can identify that equation that's not in our data booklet. It's important, though, because you're going to see graphs of nuclei. You're also going to be graphs of activity. It's the same equation, just recognizing that the initial amount is either original sample size and not, or if we're seeing activity, you might have to use the decay constant. This is very similar to what we saw with capacitance, except you'll notice that in this case we had, like in our exponent, we had negative t over tau, and here we just have negative lambda t. So there's kind of some similarity. 1 over tau is kind of similar to lambda. That's it. Radioactive half-life derivation. This is something we did with our capacitance, but we just want to recognize how to solve for this in case we need to. So we have our equation, n, the new sample size, is equal to n naught e to the negative lambda t. Well, what if I half my original sample size, right? And I'm just going to do this all the way through. My n naughts cancel. I get 1/2 is equal to e to the negative lambda t. I need to natural log it, so I natural log 1/2, which I'm just going to write as natural log of 2 to the negative 1, right? Same as 1/2, and that's equal to negative lambda t. You recognize that when there's an exponent -1 an exponent of -1 in the argument for the natural log, I can just pull that -1 out, and I can see that as negative ln of 2 is equal to negative lambda t, and that negatives cancel, and then I'm going to divide by lambda, and I'm going to take this and say, okay, ln of 2 divided by lambda, hey, that's equal to my half-life. That's our derivation for it. Now, when we look at graphs of exponential decay or radioactive decay, we can also compare our decay constant, or graphs with different decay constants, recognizing that a smaller decay constant means a smaller probability, right? So this is a less chance of decay in red, and you can see it taking more time to reach a half-life or more time to reach less and less nuclei, whereas this large is a larger chance of decay. Just important to recognize that those are our comparisons.